All right, hey everybody. We're going to try to go over a couple things. I'm going to show you a video in here, uh, mainly is what I'm going to show you, and then just talk about it a little bit as he talks about it. So, um, three-phase power. We're going to kind of tie in three-phase power and then different voltages. Probably something we could cover even more in basic circuits, but I think at this point you'll understand it a little bit better. So I'm going to pull up a couple things here. Um, so first of all, what is three-phase power? So single-phase power is when you're dealing with 120 volts, 230 volts normally in residence. So you've got what they call split phase, where you got two different wires coming in off of the same phase that's powering up most residential and most light commercial buildings that are receiving just single pole or single phase power, and they're just taking that power and they're running it in two different ways to where it's equal and opposite legs, equal and opposite polarity of the same leg. So power is coming from uh, the power plant or wherever, however it's coming in on three phase, and then they're just grabbing one of those legs, running it through a transformer, and then they're splitting that phase two different ways, and so they're running it into your house as two legs of 120 volts of the same phase that are completely equal and completely opposite. And so on a breaker box, you're going to have two sides, left, right, two different buses, and those breakers are going to be tied in to each side so that it's grabbing, if you got a 240-volt circuit running an air conditioning unit, it's grabbing one side and then it's grabbing the other side for the other power. So L1 and L2 is commonly kind of what we refer to that. So um, not to go back through that a whole lot or belabor that, but so three-phase power is when you have three distinct legs, and those legs are automatically out of phase with each other, which means you don't need a capacitor to create that phase imbalance. They are 120 degrees apart. So 360 degrees is a full electrical circuit. So each one of these takes up a third of that, basically, because so you can kind of split it like a pie. Uh, so you see here that no one of these is at the same place at the same time, but they all have the same potential voltage. So they're going positive, neutral, negative, 60 times a second, just like anything else, but any other circuit, but they're split to where they're never in the same place at the same time, but they're never exactly opposite of each other either. So, whereas if you have 202 legs of a single phase that are split, those are going to be equal and opposite. So that's where you have to have a capacitor or something to start most of your motors, because you have to have some way to create an offset to create that phase shift. So 130 volt has a natural phase shift in it already. Or sorry, 130 volt. Three phase, I was looking at something else. Three phase power has a natural 120-degree phase shift in it already. So I'm going to pull up this. There's a couple of different things you'll want to look at. So there's an article here that kind of covers, and your book talks about it as well, about Y and delta. So two different configurations of transformers, power coming into a building, and then being stepped down to a couple of different configurations. And I'll be honest with you, this isn't something that I'm really up on, except just to know kind of this is what you have and this is how it works. So, to do this and do it right, you could ask an electrician that deals with this a lot, and they'd probably be able to tell you a whole lot more. And actually, what I'm going to do is I'm going to pull up a video from a guy who's an electrician who has a really good way of explaining this. So, some of y'all may have already seen this video, but um, let's see. So, single phase transformers, and then um, single phase transformers are just bringing in high voltage, stepping it down to low voltage. Basically, the same thing that we're going to be doing on three phase. So the differences in three phase connections is you've got a couple of different basic configurations. One's called delta and one's called Y, WYE. And it kind of looks like the letter Y. So, and delta looks like a triangle. So that's why they call them that. Um, the delta connection joins in a triangular format or a layout and the Y, they all join to a central point. So, and I know this is kind of hard to understand. It's hard for me to explain, honestly, but that's why I'm going to let this guy do that just a little bit better. But read through this article. It's got some pretty good stuff in there about this, and then it talks about like how they split each voltage. So one of the big things you'll hear people talk about is there's certain times that you can check a certain kind of circuit and get some odd readings, or how do you get a certain voltage out of a three-phase circuit? Well, you have to run it through a certain type of transformer. So in Y, normally that's how you get the 208. So in our lab, we have 208 three-phase coming into our lab, coming from the transformer, stepping down from 480, stepping down from 480 in the lab, going to 208. And so that's going through a Y configuration, giving us three distinct legs of 120 volts, 120 volt power. But between them, they're 208. So that's what we have to deal with. And that's why when we actually tap most of those units off in that room, we're just grabbing two legs of the three. And that is actually a two-phase system. So I said, really you don't see two-phase, but the way that we're doing those in lab is actually two-phase. You're grabbing two of the three legs, knowing that each one is 120 volts, and you're doing it on a 208 circuit. So it's a little bit, we're having to make it work in lab because of the way that our power comes in. So it runs through a Y transformer. We get 208 volt out on three legs a piece. Between each one of them is going to read 208, and any of them to ground are going to read 120. And then if you have a 240 volt three-phase circuit, and he actually talks about this a little bit more in depth, but you're going to read 240 between any of those legs. So I'm going to pull up this video now without going into too much more confusing details, and I'm going to let him explain this. So hopefully this plays. And I will say that I'm playing this because there is a little bit of questionable language at the end, so I'm going to try to stop it before it gets to that point. So let's see what he has to say here.
Get them from. So starting out, you're going to come across like a lot of low voltages. You're going to come across some medium voltages, and then there's higher voltages. Now, as electricians, we call them low, medium, and high, or we say line voltage, but really high voltage is talking about like 500,000 volts. And as an electrician, you're never going to come across that stuff. So just for what we run into in the field, typically we're talking about stuff under 1,000 volts, usually above 50 volts. Unless you're talking about low voltage systems, we're talking like 5 volts, 10 volts, 15 volts, 24 volts, stuff like that. So let's start out with the really low voltage stuff. You're going to come across probably 5 volts and 10 volts, maybe 15 volts DC. A lot of times in lighting control systems or energy management systems, if you're going to work in places where there's like refrigeration and there's remote monitoring, a lot of those systems work off of communication signals back and forth where they're sending like a small little 5 volt DC pulse.
Okay, so I will chime in here and say a lot of our systems, especially larger commercial systems, they can use different types of communication to their stats, and that's what he's referring to here, to where they're sometimes even using DC. A lot of times you'll see on the back of a controller or a stat that's using some sort of building automation that it will say 0 to 10 volts, 0 to 10 volts DC. So that signal isn't just on or off. It may be a partial signal to where it's 7 volts means that it needs this, but 8 volts means it needs something else. So there's a range there of voltage that it could be sending to communicate with that stat, more than just saying run the air or don't run the air. Like it's actually giving it a signal to say this is how many volts we're reading, which means it's this many degrees in the room. So it's a little more complex on those low voltage layouts.
And that's how they're signaling some of this stuff to turn on and turn off. But it's pretty rare that you're going to come across those voltages otherwise. Another one is 12 volts. So 12 volts you're probably going to come into all the time. There's LED ballasts, drivers, they're actually called drivers, not ballasts. But there's a lot of places where you're going to come across 12 volt power supplies. So 12 volts is a fairly common low voltage that you're going to come across. And then you got 16 volts. 16 volts, a lot of doorbell transformers are run on 16 volts or 24 volts. But that's the rest of these voltages as well. 24 volts is another really common thing that you're going to find in a lot of LED, like strip lighting, because you run these like LED tape, you run these strips over a really long distance. 24 volts can actually just push a lot further down the line without there being a AC or DC, or some of them are both. But we'll get into the whole difference between how AC voltages and DC voltages operate in a later video. So next we're going to talk about voltages between 100 and 250 volts. This is kind of the next class of voltages that you're going to come across, and both in single phase and three phase. So in single phase, you're going to come across systems that are 120, 240, and that makes sense, right? You've got 240 volts, and when you cut it in half, you get 120 when you have a neutral present. Otherwise, everything, all the motors and machinery would just run off 240 volts. But the math makes sense how you get from 120 to 240, right? It's just cutting it in half. You're cutting your voltage in half, less pressure. But once you get into three phase, it's kind of weird because you have things like 208, and it's like, okay, well, how does 208 factor into it? So if you have three phase, there's two different kinds of three phase services. There's either a Y configuration or a Delta configuration, and it's based off of what the power company supplies to a building, what's in the area. Sometimes in different factories and different buildings, you're going to have motors that require a little bit more torque, and so they're going to need a Delta service rather than a Y, or something that has like a whole bunch of lighting loads specifically. It's going to do better on a Y configuration because you're going to have a neutral with it as well. So there's reasons why, and again, I'm not going to get into all that crazy stuff in this video, but I just want to break down how these voltages are derived and what they mean. So when you hear 240 and 208, kind of the same thing. Really, 240 just means that you're working with a Delta configuration. The transformer that's provided is in a Delta wiring configuration. And that just means that each one of the coils inside, or each one of the windings inside of that thing, are run end to end. In a Y configuration, the centers of every single one of those coils meet up. So because they're wired in that configuration, you just get a different voltage out of it. When you run incoming power, outgoing power is slightly different. So just know that if you're ever wiring a place and all of the specs call for 240 volt stuff, and you're reading nameplates on equipment, it's all 240, 240, 240, and you realize that your service is 208, you need to say something. You need to address that and figure that out, because that equipment is usually rated within 5 or 10% of its value. So if you overdrive or underdrive those motors, you're going to burn them up over time. And something like a $200,000 CNC machine, like, that's really, really important to know. So that's pretty much it for the 250 volt and under voltage systems. Now we get into a little bit higher voltage. This is a lot more dangerous stuff, but you're talking 277.
Okay, so at that point, he's talking about residential, basic residential, and even commercial wiring, to where you just got two legs like we talked about. So pretty common. And now he's going to start talking about some other stuff, higher voltage.
To 600 volts. So 277 is very similar to 120 in a lower voltage situation. It's where there is a hot and a neutral. They're just at a lot higher potential. So
I will say this, 277 is kind of odd, but I do know of some buildings. I know that the Montgomery County school system, they use 277 on their water source heat pumps. So they're tying into this other leg here, and it's essentially 120 volt, like he's saying. You got a hot and a neutral, but it's different voltage, and it works a little different. So it's not super common, I don't think, but I do know that most of theirs run that way, so it is different.
So 480 volts is the same as 240 volts, and 277 is the same as 120. So most systems that you're going to come across that are higher voltage, you're going to have 480, 277, or you're just going to have 480. There is one other voltage class above that, and that's 347 and 600 volts. So same thing, 347 is just hot to neutral. It's just a really, really super powerful amount of power. And then the 600 is the line to line, where hot. But that's pretty much it. That's the voltages. I'm going to go on the blackboard or the whiteboard over here and sit and kind of do some calculations so that you understand like how you're deriving, some service, different windings for different transformers, and sit and break down how these different voltages come out. So first we're going to look at a corner grounded delta, and that's just a delta configuration. Again, on a delta, that means that each winding of this transformer, there's 3 windings, each one is wired end to end or in series. So with corner grounding, that means that they actually ground one corner, or where two of these meet together. So the voltage in something like this, if we're on a lower voltage system, is going to be 240 volts between each end of that winding, and it's the same for all of the windings. So you're going to have 240 between all of them, and from any point to ground, you're also going to have 240. So that's pretty easy. That makes sense, right? There's no neutral in here at all. Nothing's tapped so that you can get 120 volt load out of it. In this situation, it's corner grounded. There's only 240 volt loads that can be served with this. Another common thing that you're going to see out in the field is a center tap delta, and that just means that instead of tapping the corner where you've got two of these windings that come together, or two of these coils, you're going to tap in the center of one of them. And what that does is it gives you a halfway point. It gives you a way to split the difference of potential of one of these and have two smaller differences.
And notice, guys, this isn't something that we're going to, this is just how that it's done internally, by the people who are making the transformers or designing the system. So we're dealing with the byproducts of this, but it's good to know kind of how we're getting what we're getting.
This isn't potential. So you're still going to have 240 volts across all of your coils, 240 between there and there, there and there, there and there. But because we just basically cut that coil in half, or we intercepted the halfway point of it, it allows us to get 120 volts out of each side. So this is really common. You're going to see this. A lot of like older buildings, even houses, like there's places around here in Austin, like old lake houses, that we come across this three-phase 4-wire system where it has what we call a high leg or a wild leg, and it's usually one of the incoming wires that's coming up from the transformer. It has orange tape around it, and the reason is we have standard voltages everywhere in this system, but look what happens when we try to take voltage between this and ground. So like from here to ground we get 120, here to ground we get 120, but what happens from here to ground is you get 208, which is strange, right? Like, why?
This is what people call a wild leg. It's not the 277 that a lot of people think it is. This is what they actually are referring to as a wild leg.
But you need to understand that that's a single phase voltage. That's for one hot to ground. You're getting 208 volts from one black wire essentially to neutral or to ground. And that's really dangerous. A lot of times people will hook up like lighting loads and things like that, and you'll just fry stuff because you're running 208 volts through that piece of equipment that's only rated at 120. So understanding that you have a high leg when you're working with a center tap delta is a really crucial thing to understand. If you ever see an orange conductor in with any black, blue, or red conductors, you need to like be on alert, like, oh, there's something different here and I need to be really careful. Usually that's on B phase. There's some utilities out there that likes it to be on C phase. But again, just understand what it is. It's super dangerous. So the math behind how that works and why that works, there's a number that I've talked about before, and it's the square root of 3.
So I said before, we have 208 in our lab, but we don't have 208 like this. We have 208 between two legs, 120 on each leg. This is 208 on one leg. So one leg to ground is going to read 208. That's why it's high leg or wild leg. So like he said, it is very dangerous. And you can hook it up and fry a bunch of stuff. So you got to watch that. It's not super common, and honestly, on our end, we're working from the breaker box back. So, unless you're an electrician, you're probably not dealing with this, but still good to know.
Or 1.732. If you ever do calculations in 3-phase, you're trying to calculate the size of a transformer, or you're trying to figure out kVA, power factor, a lot of these different things, you have to use the square root of 3 when you're multiplying things. If you're trying to figure out single phase, you don't have to do that. But because of the ratio of these windings and how 3-phase operates, you have to have this extra number that we input into calculations, and it's the square root of 3, which equals 1.732. So if you ever look at voltage systems and you're looking between your line and your neutral voltage, if you multiply 120 times the square root of 3, you're going to get 208. So that's not an intended thing that happens. It's just kind of the byproduct of how this power is coming in, how the windings in that generator that's generating all of this power come together and produce voltage. So you get 208. It's the same thing if you look at a Y service. Say we've got a three-phase Y. We've got 208, between each one of our windings, we've got 208, 208, 208. And we've got 120 between each to the center tapped ground. It's the same thing. We have 120 between each one of these, between this leg and ground, this leg and ground, and this leg and ground. But if you take 120 times the square root of 3, you get 208. So that's just to understand how that number works. 480 volts is the same way. A lot of people that start saying like, okay, well, how the hell do you even get 277 versus 480? And if we look at it, just scratch all of these out and say this is 480, 480, and 480. Well, 277 times the square root of 3 equals 480. And it actually probably equals like 479.25 something or other. But you get the idea. And I don't just know that. That's something like you can do the inverse of it. Divide 480 divided by 1.732, you get 277. So that's where these weird numbers come from. When you see 208, 230, 240, 277, it kind of gets confusing and you're like, well, which one is what and how are we doing this? When you're actually out in the field, it's not really that difficult because you've got wires that are certain colors. If you're working with brown, yellow, and purple or brown, orange, depending on what municipality you're working in, you know that that's a certain voltage system and that's going to be 480, 277. If you're working with red, black, and blue, you know that you're going to be within the 120, 240 range, and that includes 208 as well. So hope that cleared it up. Three-phase, single phase, same thing. You can still have 480 volt and 277 volt in single phase, and in three phase you can have 240, 120 in three phase and single phase. All right.
So that is a really good explanation. I think it helped me looking at that. So I'm kind of gonna leave it at that, but try to look over some of this stuff. That gives you an idea of why we have the different voltages that we have. And we also understand that because of Ohm's law, like if we increase the voltage, we can decrease the amperage, which means we can decrease the wire sizing, which makes the system run a lot more efficiently on smaller wires. So easier to transfer power, voltage is the force, right? So if I increase the force pushing it, then I can push it a little easier. So I'm just kind of going to let that hang there and let you guys look over that, but I think it's pretty good. So I will talk to you later.